Hello there everyone. Today I'm going to be showing you how to create a carbene. Specifically, it's going to be a nitrogen heterocyclic carbene, and we're going to be starting from our imidazolium salt. Let's get started. So, like I was saying, the goal of this is to deprotonate our, in this case, bis imidazolium salt, but this method is going to be in general for creating carbenes, just generally. We just happen to be using a bis version. So we're going to be using KHMDS as our base, and it's going to be in ether. And I'm going to be talking a little bit about why we're using KHMDS and also why it is important that we're using ether as well. So really quick, just a few challenges for this reaction. One is that these protons right here are not too acidic. I listed it here. They have a pKa of about 20 to 24. And as a reminder, pKa is a measure of acidity, where the lower the value is a stronger acid, but the higher value means that its conjugate base is going to be stronger. So we can use this to assess our acidity of our protons and of our base, and we can see which bases we can use to deprotonate to make our ligand. And the second challenge we face is that KHMDS is a pyrophoric. So you're going to need to use it in a glove box with an inert atmosphere. And as a reminder, a pyrophoric will spontaneously combust, and in this case it will react with air. It definitely reacts with water as well, because water's pKa is much lower than that of KHMDS, which I'll show you in a moment. And so it can easily pull those protons off of the oxygen. And it is it's an exothermic enough reaction that it creates enough heat where it can just spontaneously ignite itself. Since when I show you the structure, you'll see that there is some fuel source, and it'll ignite any carbon sources around it as well. So the structure, and here's some structure and some info on why we're using KHMDS, since it's pretty much the only reagent, or is the only reagent we're using. First, KHMDS stands for potassium hexamethyl disilazide, or maybe makes a little more sense to call it bis trimethyl silylamide, and it's a derivative of another more familiar strong base that I'll show you in just a moment as well. So it is soluble in most organic solvents like benzene, toluene, or ether like we're using here, and that's mostly because of these groups, the TMS groups here. They're very nonpolar, and because of the methyls, and they will easily dissolve in a nonpolar solvent. And of course, the pKa is about 26, so it is sufficiently strong to remove those protons that I showed you earlier. Comparing it to its analog of sodium amide, sodium amide only has protons instead of the TMS groups. That changes it to be much less soluble, or not soluble, in organic solvents, which wouldn't work for our reaction since our pre-ligand, the imidazolium salt, is soluble in ether. It also has a much stronger pKa, it's a much stronger base, much higher pKa of 38. And just to recall, the pKa of the carbene protons, or what would become the carbene protons, is about 20 to 24. So this is excessively strong and could lead to side products that are undesirable. This is much more ideal since it's just strong enough to remove those protons. And here is the mechanism. It's a pretty straightforward mechanism. The KHMDS acts as a strong base, a strong bulky base, so it should just be acting as a base and not as a nucleophile. And it would remove this proton right here, and those electrons will come back onto this carbon, which will then become the carbene. And the pi electrons here will move back onto the nitrogen and regenerate the lone pair on the nitrogen. And continuing down here, we do lose the protonated version of KHMDS, and the process repeats itself here. So again, you can see the proton comes off, electrons go back onto the carbon, pi electrons go onto the nitrogen, and then we're done. We have just, this would create our ligand, and these right here, this lone pair on the carbon here is what makes it a carbene. It is neutral, which a lot of people don't expect, but there is 4 electrons here, and carbon has 4 valence electrons, so the charge is 0. And if you homolytically separate this bond, you get one electron. Same thing over here, 1 electron, and then these are 2, so you get 4. So while it is neutral, it still does not have a full octet, so it's rather reactive. And the reason that we can isolate this type of carbene as opposed to others is because of how this works. So the nitrogens that are adjacent to the carbene can actually donate electron density through their lone pair into this empty p orbital right here. And if you look closely, you can see that this the carbene is sp2 hybridized. It's bond here, and then we do have one more filled orbital here with a lone pair, which leaves this remaining orbital, p orbital, empty. So it can receive electron density from the nitrogens. There is also an inductive effect here because the nitrogens are more electronegative, and the overall result is just a more stable carbene. And as a result of this being a more stable type of carbene, we can actually isolate it. And what does that mean? It means we can use it for chemistry. So one of those applications for chemistry is coordinating to a metal center, which is probably why you're creating the NHC in the first place. And just to give you a quick idea of what kind of a ligand it would be, it was previously thought to be just a sigma donor only, a strong sigma donor coordinating with that lone pair on the carbene. But more recently, the newer research shows that there is some pi accepting ability from this mostly empty p orbital on the carbon, or carbene. So that's wrapping everything up with this part of the video. Please stay tuned for the next part where we show you how to do this in the lab. Thanks for watching. Alright, welcome back everyone. So let's see how to do this in the glove box. So first, you are going to be adding some ether. We're going to be using typically anywhere from 1/3 to 1/2 of a vial's volume of ether. And just to point out, you're going to want to keep that ether or any solvent bottle in front of you and preferably towards the back of the glove box. If you put it in front of one of your gloves, you run the risk of knocking it over, which would be a huge mess and not good for the glove box. Anyway, so that was about 1/2 a vial or about 1/3 of a vial of ether, and then we're going to add a stir bar in because the reaction needs to be stirring to help facilitate what's going on. And as a side note, we're going to be reusing that ether pipette, so instead of unnecessarily disposing of it, let's put it aside. In the front is just fine, resting as it is shown. And up next, we are going to be adding the KHMDS. We have a specific graduated cylinder for that, and so that's what we're going to be using. So it should be clean. And be very mindful of how you place the bottle of KHMDS. It would be a huge headache if it got knocked over, and we're definitely going to minimize any kind of spilling by keeping the pipette over the graduated cylinder or the bottle at all times. And right now we are looking for that meniscus. We can keep the pipette right in there. Since again this graduated cylinder is used just for KHMDS, it should be clean enough to put any leftover KHMDS back in the bottle. And we're done with the KHMDS now, so we're going to close that up and put it back where it was. And we are going to slowly add in dropwise the initial volume of KHMDS. We don't want the reaction to go too out of control too quickly and cause side products. So we're going to do the first drops initially, and then you can increase the speed as the reaction progresses. And as something I don't think I pointed out earlier, this video is sped up a little bit, so if it seems fast, it's not you, it really is. Okay, and here we are going to rinse our graduated cylinder 3 times with more ether using that pipette from earlier. So we're going to do, I don't know, about a pull of a pipette's worth of volume in each time, and we're going to rinse the KHMDS pipette a bit with it, and also the graduated cylinder, and we're going to put it into the reaction flask just so we get all of that residual KHMDS. And remember to minimize spilling or drops, and we're going to keep the pipette over the vial or the graduated cylinder at all times. And put the ether away now that we're done with it. I think this is the last wash we're going to do. Okay. And so right now, we're going to let it stir for anywhere between 30 minutes or 2 hours, depending on the procedure. And thanks for watching. See you later.